Dear ladies and gentlemen, it's a big honor to give the Kelly Lecture here in Cambridge today. Our topic is the sustainability of metals and alloys. I do this work together with a couple of fine colleagues, and I will highlight their contributions as we go along. When we walk through a library and look for books related to this topic, we find a couple of fantastic works that actually come here from Cambridge, such as, for instance, the books of Michael Ashby, of Julian Allwood, and Jonathan Cullen. So I, so to say, carry coal to Newcastle, but I hope I can contribute a few thoughts along these lines. So the assignment is clear. We have to reduce the consumption of energy and the emission of greenhouse gases. We have indirect sustainability measures to do that with materials. For instance, high-strength materials that reduce the weight of cars, or magnets that enable electrical vehicle drives. We have turbine blades that allow more efficient machines, and of course, catalysts. But the big contributions, particularly to the CO2 emissions, come from primary synthesis, characterized here by the ore or by the scrap recycling, but we also have scarcity, such as, for instance, rare earths, lithium, or copper, which are elements which are not only energy consuming to mine and produce, but they're also very scarce. So metals have been in the past been part of the environmental problem, and in the future we hope to become part of the solution. Now, these problems do not stand alone, but they are entangled together with a couple of related topics. So the circular and sustainable production has, of course, to do with reducing the CO2 emission and replacing fossil fuel by green energy. Also, the entire transport and the industry drives towards electrification, and we render processes and workflows digital to make them more efficient. And we envision that hydrogen and hydrogen carriers will become very important ingredients of our future sustainable economy. And this entanglement shows that sustainability is indeed a system science. I try to put this here on the slide a little bit more in context. Here you see, first of all, artificial intelligence and digital material flows that enable higher efficiency of materials, processes, and workflows. Then we have materials for electrification that, of course, enable these current technology trends, such as, for instance, electrical vehicles. The same applies for sustainable energy sources, like windmill turbines or solar cell absorber, or materials for electric conduction. And all these materials must be studied. A very big fraction of sustainable material science is to make materials long-lived. That means the enhancement of corrosion resistance or resistance against hydrogen embrittlement produces materials with higher longevity, and that is one of the very important cornerstones of this field. A somewhat new idea is maybe to design materials that carry the gene of infinite recycling already in them. That means we must design alloys that are more robust against recycling and accumulation of tramp elements. But last but not least, we have the sustainable use of resources in the material value chain, because we must appreciate that a full circular economy is maybe out of reach, because the growth of the international markets mean that at least 1/3 of all materials must still be produced in the best of all worlds from their minerals. That means even under the best of all possible circumstances, we are dealing with about 2/3 maximum of material that can be subjected to a circular economy. And 1/3 coming from primary sources, from primary synthesis, is indeed the fraction that causes the highest emissions of carbon dioxide. Now, in terms of efficiency, industry and transport cycles have already become quite good, as you can see from this diagram. So the carbon intensity and energy intensity have become actually better. But the huge growth in population, here calibrated as a linear function, plus particularly the gross domestic product increase per capita are the real drivers behind this market growth. Another growth factor of these markets for materials are, of course, the green technologies themselves. This diagram shows, just as an example, the enormous consumption of concrete or steel or copper when you think about the production of a 3 megawatt turbine. That means making sustainable energy or providing machines that allow you to tap sustainable energy are in themselves very rich in the consumption of these materials. And that applies also to other green technologies such as solar or electrification. Another point is, and an important driving force of the international markets is that 50% and actually more of that of all the world's steel production goes still into construction. And due to the growth of the GDP, construction goes on and will go on in the next 20 or 30 years. In a worst case scenario, when global warming goes on, we will also encounter increasing tides, and that means we will have to protect our coasts and cities against rising waters. That means we have a 5-fold acceleration in the material consumption due to population, GDP, green energy infrastructures, general infrastructures, and maybe even coastal protection. The good message, however, is that most of these factors can indeed be influenced by materials. This projection is quite realistic, as you see here from an OECD calculation, which shows that the consumption of raw materials will actually double by the year 2060. And this applies, for instance, particularly to materials like iron, copper, or other metals. Again, a good message is shown here on this diagram, where you see that across all these different sectors like energy, industry, transport, and so on, about 80% can be influenced by materials and processes. That means our field has a very high leverage on improving sustainability. The indirect effects of sustainability, just to give you an example in which sectors these materials play a big role, is shown in this view graph, which was motivated by a very nice similar image in the book of Mike Ashby. What you see here is a typical cycle from a primary energy source towards a machine at the end which delivers forces to make parts. We see here that along this value-added chain, we need all kinds of materials that have a big indirect effect on sustainability. For instance, corrosion and hydrogen-resistant alloys on the primary energy side. We need high-temperature alloys or hydrogen-resistant alloys or thermoelectrics for the energy conversion and so on. Particularly, the energy conversion is typically an area where most of the energy is lost. Another aspect, as I've already pointed out, is scarcity. Many of the materials that we urgently need for a more sustainable economy and transportation are actually quite rare. And you see here from this color code that some of the elements encounter a serious threat during the next 100 years. Among them are elements like zinc or silver or gallium. What is really interesting that some of these really important and strategic materials that are shown here, particularly in red color, have actually, as we can see from this nice paper, a very low end-of-life recycling rate. That means some of the elements that we need really urgently for new technologies and for sustainable technologies are practically not recycled. So again, a lot of headroom for improving. So the punchline is, how do we tame 2 billion tons of metals per year? This number sounds gigantic, but it's actually the true number of metallic materials that is produced every year. And that comes with a big environmental burden. Metal production stands meanwhile for about 8% of the global energy consumption. We use about 2.5 billion tons of ores every year. And these productions stand for about 1/3 of all industrial greenhouse gas emissions. So these are really staggering numbers, But again, the good news is that even tiny scientific steps can have a huge leverage. So it's definitely worth working in these fields. Sustainability needs quantification. What does that mean? Here's just an example of a simple life cycle assessment framework for the case of one part of iron making. So this is the first part of iron making where you see a coke plant, sinter plant, blast furnace, and the oxygen converter. And here you see, marked by these arrows, the different fluxes of feedstock, raw materials, electricity, gases, and so on. And you have gates among all these parts of that plant, and you need to really calculate all the inbound and outbound fluxes with respect to quantifying what the real efficiencies and the real sustainability factors of each of these parts of the plants are. This is very important because otherwise these argumentations and discussions turn out to be sometimes a bit hand-waving. So the quantification must go over the entire product life cycle, of course, and that makes it also so hard for industries to arrive at joint quantification measures, because some parts of a production chain have a very high carbon dioxide footprint, while others may look very good when you deliver your material to the customer. And that's why it is hard for companies to agree on joint measures. On the other hand, there's already now pressure from the customer industries. Just to give you an example for a typical auto part, for an electrical vehicle, for instance, we all know that we must deliver mechanical information, mechanical data for the manufacturing process. We also need to tell the customer the functional properties, like corrosion, longevity, acoustics, and so on. But we currently also encounter a situation where customers want to have all the information about the sustainability. So what is the recycling rate, what is the carbon dioxide footprint, and so on. So these things are already in the making, and we must find measures to quantify them. This is just a little example. We all know that aluminum cans used for drinking have typically a rather good carbon footprint because they can have, in many parts of the globe, relatively high recycling rates. But you must quantify that quite exactly. Look at the upper bound, which actually does not look so good from the CO2 emissions. This is an example where the can was produced by only less than half recycled material that was being used in the melt and by the use of fossil power. The best case scenarios when you have a very high recycled content and likewise use a very high recycling rate after usage of the can. And you see this relationship, which goes down to about only 5% in the best of all worlds, relates roughly to the relationship between the aluminum oxide embodied energy when you produce the material mainly from the raw material, as opposed to the relatively low electrical energy that you need when you remelt the material from scraps, because aluminum has a relatively low melting point with only 660 degrees centigrade. We must also consider that there are many and quite often unintended consequences. The fact that sustainable energy sources like windmill turbines or solar cells help us making industry and transport and households more sustainable does not mean that the machines themselves are sustainable. So that must be taken into account, as you see from this use of blades in landfill. Or the question still is pending what to do with the scrapped solar cell panels, which contain many precious elements such as silver, copper, and silicon. That means we must also in the future take more care of the sustainability and circularity of the green technologies themselves. This includes also many other facets and categories, such as avoiding slave or child labor. Another point is deep sea mining. Due to the scarcity of some of the element and the growing prices, for instance, for copper or for cobalt or for nickel, now deep sea mining is becoming commercially more viable, but we start, of course, doing things at 4 or 5 kilometers depth, of which we do not exactly know the environmental consequences. So driven by the electrification trend, we start doing things that might be harmful for the next generation. Another aspect is the not sufficiently tapped urban mining. You can get 1 kilogram of gold out of about 200 tons of ores when you take a very good gold mine, for instance, in South Africa. You can get the same amount, namely 1 kilogram of gold, also from 3 to 4 tons of mobile phones, particularly from the integrated circuits. And the similar arguments apply for platinum group metals. And that means here's a big opportunity in urban mining. And currently, however, we throw away about 50 billion euros worth of electrical waste every year without using it or subjecting it to recycling. And most of these materials end up as landfill, for instance, in Africa. And often children work in order to retrieve at least the copper back from these materials. So there will be about 18 billion mobile devices on the market by the year 2024. 75% of those are not collected, and if collected, less than 20% are at all recycled. That means there's again a lot of headroom. When we look at the recycling of electronic and electrical waste, this is also not yet very mature. What is mainly retrieved is the copper and the gold. So typically you either just crush these scrap parts and melt them to get the copper directly out of a melt shop, or you subject them to a hydrochloric solution to electrolysis. And then from the cathodic part you get the copper, and the anodic mud contains the gold, which you can subject to a second electrolysis. But this is not yet all very mature and could be improved to also recycle the many other precious elements that are in these integrated circuits and mobile phones. There are also very interesting alternatives using biomining for getting these precious metals back. Another very important point is not just the energy and CO2 footprint that we already discussed to some extent, but also the enormous quantities that are being scrapped from metal production. That has very often to do, particularly for aluminium and for titanium, with the fact that many parts are chipped out of the full block rather than being made by sheet forming. Now one could argue from that information that it would be much more viable and sustainable to make parts by additive manufacturing, but also additive manufacturing has drawbacks, as it is a relatively expensive production method, particularly when you go for mass-produced parts. And also the powders cannot be used endless, but after a couple of runs you have to rejuvenate them also, and otherwise the parts might become oxidized and brittle. So as I've already said, we discuss sustainability of metals along two strands, namely metallurgical processes, which we call direct sustainability, such as the use of hydrogen as a reductant in the steel industry, or through metal products, that is indirect sustainability, such as, for instance, magnetic materials for electrification or high-strength materials for lightweight design. Just as an example, if the Eiffel Tower was built today, it would require 75% less steel for exactly the same design. That shows you how impressive the progress in high-strength materials has been since then. This is a quite impressive example of a chassis without the hang-on parts, which consist of high-strength aluminum, iron and magnesium, and has a weight of only 270 kilograms. And that, of course, scales, as you all know, directly with the fuel consumption, whether it's electrical or gasoline. That means weight reduction in the transportation sector is very important. However, we must take the next step. Look at this example. Here you have a typical mass of a mid-size SUV, 1.7 tons. And the first step, the first assignment was to massively reduce its weight, as you see here, by using higher strength materials. These can be high-strength steels or high-strength aluminum alloys. But the main point of this slide is that you also now in the next step have to take care to make these high-strength materials by sustainable production methods, for instance from scraps or from hydrogen-based iron ore reduction. And then you can count or calculate how much reduction you do not only have in weight, but also in the CO2 and energy footprint when you make these materials. And these opens up new categories for quantifying high-strength materials for the market. One of the biggest factors is, of course, the loss of material due to corrosion. That means when you want to do something good for sustainability, you should work on corrosion or hydrogen embrittlement. This is shown nicely in this diagram, where you have the production cycle that we discussed before, here for the example for steel, but you have a wide distribution of lifetimes for the different products. When you think, for instance, here of the Brooklyn Bridge, that building is 150 years old. That is very good from the longevity perspective, but before you get it back, you also have to wait 150 or more years before such materials would enter the scrap market again. So this must be built into consideration regarding scrap markets. Here are some other nice examples like the dagger of Tutankhamun from meteoritic iron, or a Hittite sword which is 3000 years old from the beginning of the Iron Age. So the good thing is, of course, that in our field we have a gigantic global market for materials, namely more than 3,000 billion euros per year. That is very good, but our assignment is the question how these markets can be turned into circular ones and how they can be rendered more sustainable. And we, of course, as researchers want to know what are the basic research questions. When we look into Scopus, then we see that there are more than 40,000 papers every year on climate change, on the science of climate change. But when you look how many papers are written on sustainable metallurgy, you have maybe between 100 and 150. And the similar numbers apply for scrap recycling. When you look for papers that deal with the science of scrap recycling, you maybe find about 300 papers. So that means there's lots of headroom for basic research to not only study the effects of CO2 emissions and energy consumption on climate change, but also to find solutions for solving these problems. In the Gates notes of the blog of Bill Gates, you find the comment, whenever I hear an idea for what we can do to keep global warming in check, I always ask, what's your plan for steel? So let's go a little bit deeper here and give the man an answer. So we already saw that the market for steel is growing enormously. So towards 2015, we envisage consumption of about 2.8 billion tons of steels per year. This incredibly large amount of material is a big environmental burden because the primary synthesis of iron from its ores, like here hematite, is made by carbon carriers. That means a reductant are carbon carriers to produce your iron, and that gives in the mass balance the very high CO2 emissions. And that is the reason why iron and steel making stand for about 8% of the global CO2 emissions. When we look just at the thermodynamic limits, we see that we have about 6 megajoules per kilogram that is embodied in the iron oxide. That is the thermodynamically stored energy of the iron oxide. When we, however, measure from the cradle to grave the total energy that is required to make iron, we talk between 20 to 35%, which is actually quite good compared to most other metals, but it's much less compared to the embodied energy. That means most of the energy is here lost as waste heat, and that applies for many metals. So one solution is reducing the iron ores with hydrogen instead of carbon carriers. And this overview compiles a couple of options that we have. In the center, you find the raw materials, scraps, fines, and lump ores, and you can subject them to reduction cycles with a couple of reduction means, like different types of molecules, like hydrogen or ammonia. You can use electrons directly, you can even use protons or ions. And they can have different aggregate states like gas, solid, liquid, or plasma. And that means you, from these considerations, you arrive at a number of different possible processing pathways, how you can reduce iron. And each of these processing pathways, of course, has an individual energy and CO2 and hydrogen footprint that must be considered. Let me show you a few examples about hydrogen-based direct reduction of solid oxides that are exposed directly to hydrogen. So this is a typical overview of integrated steelmaking, and we just only look at this part where we use iron ore subjected to direct reduction. However, we use hydrogen and not like typically methane gas. And from that we get iron sponge, which is then melted down in electric arc furnaces. Here we have the kinetics at 700 degrees centigrade under hydrogen atmospheres. First you see the very fast reaction rate from hematite to magnetite and from magnetite further to wüstite. But as soon as you get into the wüstite reduction state, and the wüstite is of course then further reduced towards iron, you see that the reaction becomes very, very sluggish and becomes slower and slower as you go along. So here's a very nice environmental microscopy observation from our colleague Professor Mark Willinger from the ETH in Zurich. And you can see here that a film of iron is formed on the oxide. So you see below is that coarser oxide, and on top of that, when you expose it to hydrogen here in the electron microscope, you see how this iron film forms. So that also means that further hydrogen or oxygen transport in the other direction must go through this iron layer. This is shown schematically here. That means the oxygen from the wüstite must escape through that iron layer towards the surface where it can recombine with hydrogen to form water. This is the current picture that we have about this process. However, when we really look into the microstructure, you see that things are much more complicated. You see here there are very different microstructure features that form. For instance, the ferrite with delamination that you see here. Here's the ferrite formed on the core region of wüstite, but you also see cracks, delamination, and very complicated substructure features. These are microstructure taken after 10 minutes at 700 degrees centigrade under hydrogen atmosphere. And here you see even that very complex, in the electron channeling contrast imaging, that very complex dislocation substructures form. This has to do with the fact that these different oxide states and also the metal states occupy very different volumes, which gives rise to the fact that you do not only form massive pore structures during the reduction, but you also build up very high stresses. This shows a view graph from a single crystalline wüstite from the surface towards the center, and you see a gradient in the porosity. For the reactions close to the surface of the oxide, you see that the material can really leave the free surface. In the center, however, the mass balance leads to a massive porosity formation in the center. This also changes as a function of the reduction time, as you see here in this view graph, with a couple of snapshots at 700 degrees centigrade. After 2 hours, you can see that the material consists of a very, very complicated microstructure with dislocations, grain boundaries, pores, and cracks. Now, if we walk through such a commercial pellet, this little oxide piece that is an agglomerate of fine ores is called pellet, and it's typically used in direct reduction. When you cut it open, you can subject it to all kinds of microscopy mapping techniques, be it chemical, structural. You can look at the phase, at the distribution of the grain boundaries, and so on. So the same things that you would do in ordinary materials, and then you get these very complex microstructures revealed. Now we are interested also to subjecting them to a boundary condition treatment here through a corresponding phase field calculation. And in this phase field calculation you can see the diffusion of the hydrogen, of the oxygen, and you can see the formation of the water as a reaction product. In this diagram you see how the iron is starting to penetrate the former oxide. Now the next step, this is again a collaboration with the colleagues at the ETH, here with Malte Erik Beer in Zurich, and we try now to study these things also in quasi two-dimensional wüstite films, which we again subject in situ to a hydrogen atmosphere, and then we study how the iron is really forming between the different wüstite layers. And that under reduced dimensions in quasi 2 dimensions. Here you see how these very beautiful shapes of the iron nuclei are forming. We also look at the characteristics of these pores that form at very high resolution. This is high angular annual dark field imaging. And through this electron tomography, we aim to study not just the dispersion, the distribution of the pores, but also how they are connected. That means how they percolate. This is a very important information that we need to better understand how the gas transport in the material takes place. Here you see a complex polycrystalline structure around such pores that form. And you can see that many of these pores are actually highly isolated. That means they are not connected so that the water that forms on the inside these pores cannot leave the material but stays in the material. And that is quite interesting. If you look a little bit more into the detail, you can see that close to the surface of the material you have body-centered cubic iron, a few pieces of wüstite here and there. In the middle you see around some of these pores actually very high concentration of wüstite directly at the border to these pores. And we interpret this observation in terms of the high partial pressure of the water that has been formed inside of these pores and that could not leave the material because these pores are not percolating, so that this very high water pressure which builds up inside of these pores leads to reoxidation of the material back to the oxide. We also go to the near atomic scale by using atom probe tomography for these materials. Here you see that before the reduction you see just the wüstite material, that was a wüstite single crystal, and after reduction or after partial reduction you see here the iron, BCC iron that has formed, but you also see due to the gangue the chemical tramp material that was in these ores. You see that some of these oxides have prevailed and remain in the material, and we study their role for the formation of water, for catalysis, but also for the delays in the reduction kinetics. An alternative and for us very exciting route of production can be to just ignore all these many processing steps and go directly from the iron ore to the electric arc furnace, but expose the ore in that electric arc furnace to a small partial pressure of hydrogen. So these electric arc furnaces, as you know, are frequently used, for instance, for stainless steel making from scraps. Here you see these gigantic graphite electrodes that typically are used for melting down the scrap. But here we have built a little reactor where we do a very similar experiment. We flood the reactor chamber with argon and add about 10% of hydrogen gas. And then we ignite the plasma in the material, and we do it always for durations of 1 minute. Then we stop the processes, take the specimens out and test them regarding the iron content that was formed, put them back into the oven, flood the oven chamber with the same gas mixture and ignite the plasma again. And by that we could show that after already 15 minutes and definitely after 20 to 30 minutes, you have under these conditions produced pure iron directly from the ore. And we found that a very interesting and viable alternative to the direct reduction by using hydrogen, because here the efficiency of the consumption of hydrogen is very good. And secondly, also if you go through the direct reduction route, at the end of the process you must put your iron sponge that comes from the direct reduction anyway into such an electric arc furnace. And here you see also beautiful microstructures that form under such conditions. And again, we do also here atomic scale analysis and see, for instance, here a very interesting interface between the wüstite and the alpha iron. So this is a partially reduced material with some remaining wüstite, and you see that the silicon that sits on the interface between these two phases seems to play quite a big role. So that, of course, in the further research we have to take the chemical composition of the oxides into account and the slag metallurgy in the secondary or ladle metallurgy. Here I borrowed this picture from a nice paper from Berg-Thorsen from McGill University in Canada. He and other colleagues suggest that metals can also be burned and used as fuel, which you then can recycle. That idea is really interesting when you look at this diagram where the energy density is plotted against the specific energy. And here metals are really very viable and have in part much better properties than established energy carriers like diesel, gasoline, or hydrogen. So the idea is that you use powders of metals, like for instance iron, combust them in a chamber, get that energy out, and then subject these powders again to a reduction process and use them again. So the first pilot plants have, for instance, already been realized, for instance, at the university in Eindhoven in the Netherlands. And these topics are of course related, and we started to study some of these microstructural features also. Now a few words also about aluminium. I already mentioned before that there's a very high discrepancy between the primary energy you need to make aluminum from the ore and the very low energy that you need when you make it from scrap due to the low melting point of aluminum. And this amounts to only 5% of the energy compared to the primary synthesis. However, aluminum alloys cannot be mixed very well. And you know we have a couple of very big aluminum alloy classes, such as for instance the cast blocks that have a very high silicon content. We have the famous aluminum copper alloys that are used for high strength plane parts, for instance. And we have also scraps that come from mixed components of aluminum and iron, which carry a very high iron content, which is typically very undesired for aluminum. That means a very high burden in the aluminum industry when it comes to scrap recycling lies in a proper sorting of aluminum. And over the cycles of recycling them over and over again, we see in part, like in this atom probe tomography measurement from our lab, that some of the elements start really to accumulate in this material. This here is a packaging material that contains about 15 different elements that we find in them. That means for some high-end packaging application, this material can no longer be used, but it also shows nicely that a very interesting option for research in the field of aluminum consists in identifying alloys which are more robust against cramp elements as these accumulate over the recycling cycles. So that is, so to say, the science of less pure materials. And of course in aluminum alloys, particularly the iron is a big problem because it forms also brittle intermetallic phases, and one can, for instance, when you tolerate higher iron content in aluminum alloys, try to change these intermetallics by further alloying in order to make the overall scrap containing alloy more robust towards recycling. The basic question that of course comes from that is whether we at all have already too many alloys on the market. When you see this nice diagram, then original systems were satisfied with a small number of elements from a periodic system, while modern gadgets like wind turbines or mobile phones use already up to a third of the periodic system. Even in the field of alloy design, we see a trend towards using a higher number of principal elements, such as, for instance, in the field of concentrated alloys, metallic glasses, or high entropy alloys. And that is a trend which is maybe not entirely compatible with the field of sustainability, or when you do so, you must maybe gain or produce properties that you cannot achieve by other materials. So principally, that shows us that, of course, mass and energy are conserved quantities, but microstructure and properties, the main cornerstones of our field of material science, are not conserved. And that is a very good message, because by microstructure design and heat treatment and forming processes, we can create new microstructures and can rejuvenate established microstructures, as you see with this little movie. This is shown here for the case of aluminum alloys. We plot here the tensile strength of aluminum alloy as a function of the overall alloying content. And you see here the main aluminum alloy classes like the 1000 alloys, which are relatively pure and used for packaging. We see the manganese containing 3000 series alloys also for packaging. We see the higher strength 5 and 6000 series alloys that you, for instance, encounter in car design. And we see really high strength 7000 alloys that you use for plane components for cars, but also for mobile devices. And on the one hand, we indeed see a certain clear trend that the tensile strength of these alloys increases with the overall aluminum alloying content. But on the other hand, you also realize that there's a huge scatter for each of these alloy groups. That means there's a big range for the tensile strength in this case that can obviously be influenced by microstructure and by processing. And that means in the future we should maybe try really to design a higher variety of materials, not through chemical variants, but through microstructure variants. And when I put that a little bit in an overview diagram which shows technology readiness of the different measures against potential for impact, then I already mentioned the highest impact and TRL level comes of course from longevity measures, but also by using electrical energy from renewable sources, maybe producing less scrap in the manufacturing, and of course the indirect effects that we get, for instance, from catalysts, from scalable energy materials, and so on. Maybe with less technology readiness, but maybe with a very high potential for impact, we find, for instance, plasma chemistry that can be used for alloy or for ore reduction, or all the methods that reduce material from the primary ores without using carbon carriers. And so in that overview diagram, I think one can say that some of these topics have a relatively high risk, but also a very high gain. And again, what I said in the beginning, there's a lot of headroom for basic research in all of these fields. And with that, I think I conclude here, and thank you again very, very much that I could deliver the Kelly lecture today and summarize that there are really, really big effects which deserve a lot of basic research from the material science community. When we talk about greenhouse gas emissions, energy consumption, and effects coming from mining, then definitely we want to look at iron, aluminum, and other materials. When it comes to scarcity or even toxic effects, there are many other materials that deserve our attention, and there's a lot to do in the future. So thank you very much, and bye-bye.